All right, gang, here we go. This is for Physics, Unit 9, Part 1, Video 1. We're going to do Part 1 in two parts. All right, so this first one, we're going to talk about electric charge, what it all means for us, how does it work, so on and so forth. Talk about some basic ground rules about how does electricity work, and electrical forces, and so on and so forth. All right, so here we go. So electrical charge. Now, some of this should be very obviously review. Okay, there are two types of charge, positive and negative, right? Like charges repel and opposites attract. So a positive and a positive will push each other away from each other. A negative and negative will push each other away from each other. So this is like a balloon. Now, if you take two balloons, go ahead, pause the video, grab two balloons, all right, and rub them on your hair, and then just try to push them together, and you'll notice that they'll actually push each other apart. All right, and that's because you've put this charge on each balloon. All right, and by doing so, you've put the same charge on both balloons, and so now they'll repel each other because they have the same charge. But if you take that same that balloon, and you put it up next to somebody that has long hair, okay, that hair will get stuck to that balloon and will pull it up against it. All right, and so that's because they have opposite charges now. All right, so we can transfer these electrical charges, okay, by just simply transferring electrons is essentially what happens. All right, so in a neutral atom, okay, the number of protons and the number of electrons are equal to each other because protons are positively charged, okay, and electrons are negatively charged. And if they are equal to each other, you have no net charge, all right, so you have a neutral atom, all right. But electrons, because they're not stuck in one place, they're easily transferred from one atom to the next. Protons and neutrons remain in pretty much fixed positions. They don't really get moved around too much, which is probably a good thing. All right, but these electrons can move from one place to another. So essentially, these negative charges from these electrons can get moved from one place to the next. So when you're rubbing a balloon on your hair, the electrons are attracted to the balloon and transfer it from your hair to the balloon. So literally, what happens is these electrons are leaving your hair and getting stuck to this balloon. Okay, so now your balloon has excess electrons, so it has a negative charge. All right, a negative charge, and your hair, because it's lost electrons, has an overall positive charge, right? So it's got these excess protons, and so that's essentially why those balloons, both balloons are negatively charged, so they repel each other, and then your hair is attracted to it because it's positively charged. All right. Now, Millikan was this physicist chemist, okay, and he came up with this idea. We talked about this experiment in chemistry, all right, but just to recap what was going on, he did what was called the oil drop experiment, and he had these two plates, all right, and so in the middle plate here, he put a small hole, really, 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 really small, so only the tiniest little particles of this oil could drop through, all right, and he charged these plates, okay, so that there was, one of them was positively charged and one was negatively charged. And so what he did was he sprayed these atoms, or he sprayed this oil in using what is possibly the coolest named thing ever, called the atomizer. All right, so this is the atomizer. You got to say it like that. So that when the oil drops got sprayed out of the atomizer, they got charged because of the friction of them rubbing against each other and rubbing against the nozzle. And so these electrons come out with a charge, and they're charged positively or negatively, and they fall through this guy here. And then with a microscope, he could actually see the path that these oil droplets would fall. And because they could only fit through this one tiny hole, he could easily see all these charges. And then he could change the voltage on these plates. So essentially, and that doesn't mean anything to you yet, but essentially what he's doing is just changing the amount of electricity that flows through these plates. And based on that, he could actually make the droplets slow down in their fall, or actually fight against gravity and travel upwards. All right, and so by doing that, he could actually measure the ratio of how that occurred. Okay. And by using the size of the droplets as well as the amount of voltage applied, he could actually find that the amount of charge on any object was always a multiple of what he called the fundamental charge. All right, the fundamental charge, which was E. So in other words, he found out that charge is quantized, meaning that it always occurs in discrete packets. All right, and this E value, this fundamental charge, turned out to be the charge on an electron, 1.602176 times 10 to the 19th, negative 19th coulombs. Okay, and so coulombs is the SI unit of charge with a capital C. So, so here's your charge and mass of atomic particles. Here is the electron is negative 1.6 times 10 to the negative 19th coulombs, and a proton is positive 1.60 times 10 to the negative 19th coulombs. And here's your masses and so on and so forth, just for your funsies to look at here. Protons, you can see protons are about 1,000 times more massive, 10,000 times more massive than electrons, and protons and neutrons are about the same size. Neutrons are slightly heavier. Okay. All right. So, what amount of charge does a single electron carry? Well, we just established that. That's negative 1.60 times 10 to the negative 19th coulombs per electrons. All right. It says how many electrons are needed to produce an amount of charge equal to negative 1.0 times 10 to the negative 1 coulomb. Wow. All right. So this would just be a little bit of dimensional analysis here. Okay. So it would be negative 1.00 coulombs. All right. And we'll just use this ratio we just established. So coulombs will go on the bottom, electrons will go on the top. All right, and it's negative 1.60 times 10 to the negative 19th. 1, and so that would be equal to this value. All right, 6.25 times 10 to the 18th electrons per coulomb. All right, so in order to get 1 coulomb, you need a lot of electrons. What is the mass of this number of electrons? Well, we just take our 6.25 times 10 to the 18th electrons. All right, and then we just do a little bit of math, and we're going to use this mass of electrons right here. 9.109 times 10 to the minus 31st. All right, and so then you get this for your mass right here. All right, and 5 billionths of a gram. It's a small amount. Okay. Now, conductors and insulators, we've kind of talked about this before, all right, about properties of matter and so on and so forth. You probably learned about this in chemistry. The term an electrical conductor is something that allows electrons to flow freely through them. So in essentially any metal. Metals are great electrical conductors. All right, so like silver, copper, aluminum, and other metals like that. All right, what is meant by the term electrical insulators? Insulators are the opposite of conductors. They don't allow electrons to flow through them very easily. All right, so like plastic, rubber, glass, all right, all these are great insulators, or very, very poor conductors. So why do conductors and insulators behave differently? And it's all to do with the outer electrons that are in metals are loosely bound to the nucleus. And you'll see, sometimes you'll see this referred to as a sea of electrons. So these electrons are just kind of floating, and they just kind of be able to pass from one atom to the next, be able to move from one to the next easily. All right. So insulators and conductors can be charged by contact. We're going to talk about 2 different ways to give things charged. All right. Now, we've already talked about charging by contact just with the balloon and the hair. And when you take these 2 materials and you rub them together, you get a transfer of electrons. So when you're charging metal, the charge may move through your body into the ground. Okay, the metal in your body are both conductors, so the charge moves through them. So if you hold the conductor with an insulating material, such as rubber gloves, you keep that charge on the metal. All right, so that's the trick to charging by contact. And so like taking the balloon in your hair, you're a little rubbing it together, and these electrons can transfer from one thing to the next. Pretty simple, right? Charging by contact. Charging by induction is a little bit more complicated. All right, so for example, we have this charged rod, and it's rubber. Okay, notice that rubber is an insulator, but that doesn't mean it can't have a charge. It just means that these electrons don't flow freely through them. All right, so you've got this charged rubber rod, and it's negatively charged, and you hold it near this metal sphere, and you can see that it makes sense that these negative charges, remember the positive charges don't move around, they're pretty much stuck, but these electric charges will get pushed away. They'll get pushed away from this negatively charged rubber rod. And that makes sense because like repels each other. And so you'll get these positive charge over here. So then, but notice that they're not actually touching. But because they're close to one another, you get a positive on one side and a net negative on the other. So now you've introduced a charge into this metal sphere, even though nothing's actually touching it. All right. And so this is called induction. All right. So if you took this metal sphere and you connected it to a ground, and a ground is just a place that's got a vast bank or ability to take electrons, like the ground, like the earth, okay, which is where we get the name. So you attach it to a ground, all right, so that's what this symbol means here. If we attach this guy to a ground, these electrons have now a new place to move that's even farther away from this rubber rod that they don't they have a place to go that's even farther away from this rubber rod than before, so they're able to go down into the ground. So these electrons can travel down here, and so these electrons can go down here and leave, all right? So they actually go away, and that's because they want to get farther away from this rubber rod. You take away the ground, cut it off, and these electrons cannot travel back up the wire because the wire's gone, all right? So now, even if you pull this away, now this guy has a net positive charge, all because you never actually touched it. It was just like this mere presence, and we call that induction. So by using this rubber rod, we've scared off some of the electrons, and so now when you've cut everything, pulled everything away, these electrons still spread out evenly, but because there's less of them than the positive, you get an overall net charge that's positive on the sphere. All right, pretty wild. All right, last thing here, surface charges. All right, charges tend to stick near the surface of your object, which is pretty bizarre. So you got this balloon, and it's going to be right here on the surface. All right, so you've got this let's see, it's not necessarily a balloon because balloons tend to be negatively charged, but whatever. So you got this charged object here, and you've got some insulator. Now you've got these negative and positive charges. Notice that they've kind of arranged themselves to shift, right? So the negative charge is going to be closest to these positive charges, right? And the positives are going to be farthest away. And so you form these charges that are on the surface. Overall, this insulator is going to be neutrally charged, but because these electrons can't really move from one side, or the insulators don't allow electrons to transfer very much, okay, you really just get this flip. So you get this surface charge going on, all right? So these electrons will just shift within these specific atoms, all right? And this is due to either the retraction or the repulsion of what's going on, all right? So because the negatives are going to be want to be close to these positives, you get this attraction force. So they actually get flipped around. Now notice that the insulator, once again, does not have a net charge. It's just got the surface charge, all right? And so it's pretty wild. So if you've ever had this experience here, or like if you've ever played around when you were a little kid with like packing peanuts or something like that, these little styrofoam balls kind of tend to stick to everything, and that's because they can actually get surface charges on them. So you can take, like, if you take a comb, right, and rub it through your hair, just go like crazy through your hair, and then take a piece of paper, tear it up into little spaces, take that comb you just rubbed through your hair, and your comb will actually be able to pick up the little pieces of paper. And that's the same idea that was happening with all those little packing peanuts when they got really, really small and you were a little kid and you were jumping around in them, and they'd get into little pieces and you'd actually induce a charge on them, all right? And they'd get surface charges. And so even though the net charge of that styrofoam ball was neutral, all right, it still gets attracted to this, this other part of your surface here. All right, so next video, the last part of part 1 here, we'll talk about Coulomb's law, but that's enough for today. All right, so I'll do your practice problems, and I'll see you on the flip side.